All right, and I see Jeff Gillis-Davis just dialed in. Welcome, Jeff. All right, so thanks everyone for calling in to what I think will be our final Friends of Lunar Volatiles telecon for 2021. So well done for making it through 2021. And we have a great presentation to round out the year. Kathleen Mandt, my colleague at APL, is going to be talking to us today about some recent work that she and co-authors have done on trying to understand the origin of the volatiles sampled by the LCROSS impact. So before I hand it over to Kathy, I'll just remind everyone to put yourself on mute unless you're speaking. Videos can be on or off, up to you, whatever you're comfortable with. And Kathy, would you prefer if we interrupt if we have questions, or would you prefer to hold them until the end?
Yeah, I welcome interrupting with questions. I actually only have about 18 slides, so I left plenty of room for discussion because I'm expecting a lot of questions.
Awesome, that's great. All right, so with that, I will put myself on mute and hand it over to Kathy whenever you're ready. And slides still look good. I think you're on mute though, Kathy.
There we go. Okay.
All right, perfect.
It's not as easy to unmute when you're sharing your screen. Okay, so thank you for having me here to the Friends of Lunar Volatiles. I have an insane schedule, so I've only managed to call into a couple of these telecons, but I think it's really wonderful that there is this group that gets together and talks about lunar volatiles. And I'm really excited with the future, with the Eclipse and Artemis program, the future opportunities that we're going to have for lunar volatiles, and seeing this group grow and contribute more to the science. So what I'm going to present today is a paper that we currently have in review, and it's called An Exogenic Origin for the Volatiles Sampled by the LCROSS Impact. And what it is we're taking a new look at the composition of the volatiles that were sampled by LCROSS to try and figure out if there is a way to constrain the origin of these volatiles. Now, before we go into the full details on that, to give some context for the motivation for this study is just the entire big picture of what the moon is to us. And we use the moon as a cornerstone in so many ways. We use the moon as a cornerstone for understanding the impact history of the Earth-Moon system and terrestrial planets. And what we've learned from the moon has implications across the solar system. We're also able to study terrestrial planet formation and interior evolution, things like a magma ocean history, volcanic history. And there are things that we can learn from the moon that we can't learn from studying Earth. We also are looking at the formation, evolution, and loss of an atmosphere. There's some recent studies that have been published looking at volcanic outgassing and whether that can form an atmosphere and what the loss rates would be and how long that atmosphere could last. And then we also study contemporary processes. With the future exploration in situ of the moon on the surface at the South Poles, we are moving into an era where we can use the moon to study the history of volatile delivery to the Earth-Moon system. And the study that we're doing here is not meant to be the answer to all questions about volatiles on the South Pole of the moon, but more of an introduction to a new era of exploring volatiles at the South Pole of the moon, and a way of demonstrating to the world what value these volatiles have and how important it is that we, as we have human exploration, we also take the time to characterize these volatiles and gain as much information as we can from them. So I've done a lot of studies on volatiles across the solar system, and some of the most important measurements are composition of volatiles as far as like carbon, nitrogen, sulfur bearing volatiles and isotope ratios. For the moon, most of the information that we have is water. We look at mapping water on the surface. We look at mapping water at depth with different instruments that can take remote observations. And these are very useful, but they are also limited to just water. Now, I know that there are some studies looking at LAMP, Lizette Magana, which I don't think she was on, but she is using some of the LAMP observations as part of her dissertation to see if there's a way to find other volatiles. But other than that, we're really limited in what we know beyond water in the permanently shaded regions. The one measurement that we have where we have something beyond water, molecules that have carbon, nitrogen, and sulfur, is from the LCROSS impact. Now I'm showing here two tables that published the composition of the volatiles that were observed in the plume. And the one on the top was measured by the shepherding spacecraft that followed the LCROSS impactor and measured the plume composition in infrared wavelengths. And they were able to get quite a few molecules. Now, in addition to that, the LAMP instrument also observed the plume from a different spacecraft, so with different timing and different geometry, and they observed magnesium, calcium, mercury, H2, and CO. Now, in our study, we're not looking at the magnesium, calcium, or mercury. We are just looking at H2 and CO. Now, the problem we first encountered when we looked at these two publications, and Dana Hurley had done an update to Gladstone et al., which I'm showing Randy Gladstone's table here, because the measurements that were made by LAMP were made at a different time than the reported composition from Kolaprit et al. And so the first thing that we had to do was revisit the LAMP measurements and look at what the composition of the plume was at the same time as those reported by LCROSS, which was later than the volatile composition that was reported in the Gladstone paper. So we did that and used Dana's plume model to figure out what the relative composition of CO and H2 was to water at the appropriate time. And then we can use the CO and H2 composition in addition to what's reported in the table here. Now, are there any questions before I move on to further with the study? Okay.
Hey, Kathy,
Oh,
I
yes.
I guess since you asked, I just have a super quick thing. But in the table below, what does the type column in the lower table mean? The SIL, CON?
That I am not sure. I should look that up.
Yeah, I mean, I can, yeah.
Yeah.
I can look that up as well.
But that is a good question. Now I'm curious. I'm going to look that up too. Any other questions?
A quick question, if you can hear me.
Yeah.
You said there's a difference in the timing of the measurements. How much
Yes.
is that?
I don't know exactly how
So
much.
like one orbit
Yeah.
later?
I don't know in terms of orbits. I do know that when there was immediately, what was reported in Gladstone et al. Was immediately after the impact, there was this huge plume. And that's what Randy used because that was the best observations from LAMP. But what was used for the Kolaprit observations was later on. And I don't know exactly how, how many seconds, minutes, timing for that. But the other reason that we use that, and I'm going to get into it a little bit further, is if the volatiles are stored as volatiles condensed onto the regolith, that later observation gives you a better understanding of the composition because you're getting more of what's just sublimating off of the regolith instead of the direct impact itself.
Got it, thanks.
And that comes from Dana's modeling.
Yeah, it looks like the type has to do with the volatility. The lower volatile, and maybe magnesium is intermediate, but I'm not sure exactly what it means, but
yeah, we'll talk about that a little bit more too. And I see that David Kring put a comment in the chat about limited composition. And yes, he points out that Apollo regolith samples does have some elemental and isotopic data, and that is true. What I'm focusing on, and I should have been more clear about that, is the volatiles that are stored in the permanently shaded regions. And I'm focusing on that because of treating it sort of as a time capsule of volatile delivery to the moon itself, which is a good lead in to my next slide, where we look at, okay, we have the LCROSS plume composition that is giving us information about the volatiles that are located in the permanently shaded region. And how do we connect that back in time to the volatiles or the sources that deliver these volatiles originally to the permanently shaded region? And on the left, early in time, whatever that time scale is, I list 5 potential sources for volatiles for the permanently shaded regions. And those include volcanic outgassing. That could be intense volcanic outgassing billions of years ago that could have formed an atmosphere, or it could be short-term outgassing from the interior that, even based on the 40 argon in the exosphere, suggests could be still happening today. There are also impacts of comets, asteroids, and meteorites, and these represent 2 different types of composition. Comets, most of what we know about the comet composition is the ice composition, but comets are icy dirt balls. So they're a mixture of ice and then refractory material. So a lot of the measurements that we get on comet composition come from the ices that are released into the coma, and then we measure them remotely in the coma. We've also measured them in situ on a couple of missions, particularly the Rosetta mission. Asteroids and micrometeorites are chondritic in composition, and there's different types of chondrite compositions. Now, comets, they have refractory material that would also be likely chondritic in composition. So those are the types of source compositions for those 3 sources. And then the final source is the solar wind, which is impacting the surface every time that the moon is outside of the Earth's magnetosphere. And that's delivering mainly protons to the surface. And those protons interact with oxygen in the regolith and form OH and eventually form water. So this is a source for water. It is also a source for other elements, but at much lower abundances compared to the other sources. So any questions so far? And I see, oh yeah, thank you, Jennifer. She put an explanation of the LTV and other items that were in that column. Okay, so moving on. Okay, we have this PSR composition from LCROSS, which gives us a bunch of molecules and their abundances relative to water. And then we have the sources, which we know molecular composition for a lot of these sources as well, like volcanic atmosphere would have CO in it, or comets have H2S and water and ammonia, and there have been measurements of N2. But the problem is we can't just compare molecular composition to molecular composition and have a one-to-one correspondence because of all these things that happen in the middle time. We have atmospheric and surface transport. We have chemistry in the atmosphere and on the surface that change the molecular composition of the source material to something else. There's atmospheric escape that removes some molecules more easily than others based on their masses. So something that has a lighter mass is going to escape more easily than something that has a heavier mass. And then finally, that final trapping in the permanently shaded region is going to happen through one of 2 ways. One way could be trapping in clathrates, where water forms cages, and inside those cages are other molecules that get trapped. That's one possibility, and it's possible. We explored the possibility of whether the volatiles in the permanently shaded region were stored through this mechanism. The other possibility is condensation of individual molecules onto the surface. And if there's enough heating to their volatility temperature, they could evaporate and then recondense and evaporate on potentially a diurnal scale as they're transferred to the permanently shaded region. And then depending on the temperature conditions in the permanently shaded region, that could continue. So a lot of things happen between the source and the permanently shaded region storage. So what can we do to connect these measurements that we made with LCROSS to their source when we have to figure out a way to constrain all of this stuff that's in the middle? The approach that we took is to focus on relative elemental composition. And by doing this, we were able to eliminate the role of chemistry, because we're not looking at what molecules are becoming what, like whether H2S is later converted to SO2 by interacting with oxygen in the regolith or something like that. We're focusing just on the elements that are the elemental composition of the source and the elemental composition that was measured in the plume. And so this helps us to eliminate some, but not all of those stages in that middle. And so I'm going to walk through how we approach the next step of looking at the influence on the elemental composition as well, after I go through this comparison of composition measured in the LCROSS plume with the source composition. So any questions before I go on to talk about composition? All right, so on this chart, I show the ratios, the elemental ratios that we looked at in this study. And we have in black the two possibilities for the composition in the regolith that was sampled by the LCROSS plume. In the case of clathrates, you have the water cages that are trapping molecules on the inside. And when the LCROSS plume impact happened, what would happen is what's released into the plume is the water, along with everything that was trapped inside those water cages. So if a water cage is destabilized or a clathrate is destabilized, it releases whatever's in it. So in that case, what we saw in the plume would represent what's in the regolith. On the other hand, if the volatiles are condensed onto regolith grains and just stored individually, then they would be released in the LCROSS plume based on their volatility temperature. And so something like CO, which has a much lower volatility temperature, it's more easily released, would be released from a larger area of regolith than water, which has a higher volatility temperature. And so we had to backtrack what area of regolith is represented by each of the molecules based on their volatility. And that's where we get the condensate information on what the elemental composition would be if they are stored as condensates. Now, looking through and comparing these elemental ratios with the potential sources, what we see, if we look at just nitrogen and sulfur relative to carbon, there is a lot of nitrogen and a lot of sulfur compared to carbon in the LCROSS plume. Volcanic outgassing would agree with the sulfur, because there's a lot of sulfur in a volcanic, in what's outgassed from volcanoes compared to carbon. But there is very little nitrogen in the volcanic gas. And the values that we got for the nitrogen is based on Apollo samples, which has a much higher nitrogen abundance for volcanic gas than Earth volcanoes. So we're actually being pretty aggressive in how much nitrogen we're allowing to be coming from volcanic outgassing. Now, chondrites, similar to volcanoes, it has enough sulfur relative to carbon, but is depleted also in nitrogen relative to carbon. Even comets like 67P, which is the best characterized comet, is still lacking in nitrogen. But if you take the average of comets and the upper limit of what's been measured, it is possible for comets to provide enough nitrogen relative to carbon to agree with what was seen in the LCROSS plume. However, even taking the most extreme values for sulfur measured in comets, you don't have enough sulfur to contribute or to agree with what was seen in the LCROSS plume. So moving on to the next ratio, looking at oxygen and sulfur compared to carbon. And oxygen primarily comes from water, but it can also come from CO, CO2, and SO2. Volcanic agrees again with sulfur, but volcanic gas is depleted in oxygen relative to carbon compared to what was seen in the LCROSS plume, so it doesn't have enough oxygen. Chondrites agrees very well with both of these ratios. And then comets, again, can agree well with the oxygen, but not with the sulfur. Now, you'll notice in both of these that solar is way off the chart for sulfur. It's much lower in sulfur. It does not have very much sulfur relative to carbon, and it does not have very much oxygen relative to carbon. Any questions so far before I go on to the last one? Alrighty, so the last one is introducing hydrogen and carbon relative to hydrogen. Now, as you can see, the solar wind has so much hydrogen that there just isn't enough carbon to contribute enough to explain what is in the LCROSS plume. So what we're assuming from this point on is that the primary contribution from the solar wind is hydrogen that contributes by forming water. So we look at the solar wind as a source of water primarily. We can incorporate the other elements, but it just does not contribute enough to really explain what was seen in the LCROSS plume. Volcanic agrees with sulfur again, but it's really depleted in hydrogen, as well as chondrites, but comets provides enough hydrogen, still depleted in sulfur. So we basically have no single source providing the right elemental composition. So that leads us to our next step in our study, which is modeling a combination of sources, and that we take to another level to model a combination of sources and fractionating processes. All right, so this is where it gets really fun, describing the model. So what the approach that we took in modeling the source of volatiles was we basically created a model that's a grid search. We took every possible combination of percentages of 4 different volatile sources that summed to 1, which ended up being 167,000 models, and calculated what the LCROSS plume composition would be based on that modeled fraction of each source. And we also propagated the uncertainties for each of the observations to what would be seen in the LCROSS source to see what the uncertainty, if the uncertainties in the modeled composition overlapped with the uncertainties in the LCROSS plume. And then we did this calculation of 167,000 models and looked at 6 different scenarios that are listed on the right here. And I will walk through the results, the way that we did each of these scenarios and the results from each of them. But before I do that, are there any questions about the model? Okay, moving on. So this outlines the constraints that we used for each of the scenarios when we did this modeling. And it outlines what we expected for each of the elemental ratios, what we expected the LCROSS composition to mean for each of the elemental ratios for each of the scenarios. So for example, with the no fractionation, we would have to have the calculated LCROSS composition to be with its error bars to be within the uncertainties of the measured LCROSS composition for no fractionation of the elements to have taken place. Then we looked at processes that would take place in a volcanic atmosphere. And these 2 processes were loss of sulfur to the surface through aerosols or basically being trapped in the regolith grains before it can make it to the permanently shaded region, and then atmospheric escape. Now, recent studies have definitely shown how very, very difficult it is to constrain a past atmosphere on the moon, because there is so much that we don't know about the factors that would be controlling the escape rate. And O.J. Tucker has a recent paper about that that really just brings home the difficulty for us in saying this was the escape rate at this time in the history of the moon. So we decided that we weren't going to try and take on this impossible task of determining escape rates and determining outgas rates. And instead, what we determined was how escape would influence the different ratio. Like for nitrogen to carbon, the nitrogen would more likely be lost than the species that bear carbon because of their masses. So what was measured by LCROSS, if atmospheric escape was taking place between delivery of volatiles to the surface of the moon and delivery to the permanent shaded region, that means that what was measured by LCROSS would be a lower limit for the nitrogen to carbon ratio because some nitrogen has been lost in the process compared to the carbon. And then we determined also for oxygen and hydrogen the same thing. With water, it would break apart. Hydrogen would be lost first. And so the carbon to hydrogen measured by LCROSS is an upper limit. Any questions about that? Because I know that probably sounds pretty convoluted. Okay, so moving on to the other scenarios, we took into account impact and escape. So if you have a comet or an asteroid impacting the moon, that impact itself is going to remove volatiles. That process will be similar to hydrodynamic escape, where the lightest molecules do escape fastest. But if they're escaping fast enough, they can drag heavier molecules along with it. And then afterwards, there could be some atmospheric escape as well. So for those, we have lower limits for all of the ratios based on their masses, except for carbon to hydrogen, where hydrogen is lost faster. With clathrate formation, that one's a little bit more difficult, and it depends on the process of forming clathrates. So if you have a comet or an asteroid impact and you have water forming clathrates and trapping molecules in those clathrates, and you have in the gas where the volatiles are being trapped from, you have carbon monoxide and then sulfur-bearing species, either SO2 or H2S. Clathrates preferentially trap the sulfur-bearing species first, and then if there's enough water, we'll trap all of the CO. So if there's not enough water, you're going to end up with an enriched sulfur amount in the clathrates compared to carbon. So that gives us the constraint that the carbon to sulfur is a lower limit in the LCROSS plume compared to the source if the volatiles are stored as clathrates. We can't constrain nitrogen to carbon because the ammonia would actually be condensed. It wouldn't be trapped in the clathrates or the nitrogen that would be stored in the regoliths. So it's a different form. So we didn't even use this ratio in this model. But we have another way of constraining oxygen and hydrogen, and that's based on the number of molecules of water required to form the cage and compared to the number of molecules inside that cage. And so the oxygen to carbon cannot be greater than 6.75 if you have clathrates storing these volatiles. And that also provides a constraint for the carbon to hydrogen as well. And then the last process that we looked at is sublimation and recondensation, where based on volatility temperatures, volatiles are released and then they can recondense if it gets cold enough again. And through this process, the ones that have the lowest volatility temperature are more likely to be lost because they don't recondense as easily. So we looked at the volatility temperatures and determined what ratios have a lower limit and upper limit based on those temperatures. And then finally, we combined atmospheric escape, sublimation, and recondensation. And as you can see, the oxygen to carbon and carbon to hydrogen counteract each other if you're using escape and sublimation and condensation. So we can't even use those ratios as a constraint. So we found another approach to getting better constraints on that. So after all of that explanation, are there any questions before I move on?
Hey, Kathy, I have a question, and then there's another one in the chat. But so my question is, can these fractionation processes be cumulative? So for instance, how do you account for a scenario in which, maybe you have a volcanic atmosphere, which leads to some fractionation, and then after the ice is deposited, maybe you have some sublimation, recondensation. But so did you guys account for?
So with the volcanic atmospheric processes, the main driving was atmospheric escape, which we also included in the impact and escape. And in all of these cases, we did include a volcanic source as a possibility. So we were kind of combining those. The only thing we studied really in isolation was clathrate formation. But we did try to combine in that very last category, escape, sublimation, and recondensation. And that's why we have fewer constraints, because some of them do counteract each other.
Awesome, thanks. And then MD, I think that's Mona Zalitsky, has a question in the chat, but I think the gist of that is whether radiation processing might lead to some kind of fractionation.
I think it looks like the question is about particle impacts when the moon is inside the magnetosphere compared to outside, and if there's potentially a source inside the Earth's magnetosphere. And that is a really good question. I don't think that the flux of ions to the surface inside the magnetosphere is significant enough compared to the solar wind flux, but I'm not too sure. I think that would be worth looking at. And then she does have a question about radiation processing. And I think that would be similar to surface chemistry, a totally different process, but the end result would be changing the molecular composition. And our goal was to remove a process like that by focusing on elemental composition instead of molecular. Does that answer your question, Mona? Percentage? Oh, yes, I don't know the percentage of time spent inside the magnetosphere versus outside. And that is something I should know off the top of my head, but I don't, so I apologize. That's something I will look up so that I can answer that the next time. Okay. All right, any other questions before I move on to results? Okay. So the first study that we did was no fractionation. So we did those 167,000 models, and that produced for us what the LCROSS composition should be with error bars based on that model's combination of sources. And what was really shocking to find was that no combination of sources was able to fit, even taking into account the large error bars for the sources and the large error bars for the measurements. And the reason is that no combination of sources was able to provide the right amount of sulfur and nitrogen relative to carbon. These two constraints are so ridiculously strange in the LCROSS plume compared to the sources that some sort of fractionation had to happen between the delivery from the source and what we saw in the plume. So we didn't have an easy answer, which, that's science. We're not supposed to get easy answers. So the next one was we looked at volcanic atmospheric processes where sulfur is lost to the surface, nitrogen is lost from the atmosphere, and same with water, preferential to carbon. We again found no good fit. And the main reason is the nitrogen. If you have a volcanic atmosphere and it's providing a lot of sulfur and carbon, it's just not providing enough nitrogen to match what is being measured, even assuming, especially assuming that atmospheric escape is happening, because what we're getting from the source has to be providing more nitrogen than what we're actually seeing in the plume. So And we even allowed for contribution from comets and contribution from chondrites, and we just were not able to get a match to the LCROSS plume. So from that, we are able to rule out a volcanic source or any major contribution of volcanic gas to what was measured in the Cabeus crater. And that's the top 3 meters, 1 to 3 meters of the Cabeus crater, which is what was sampled by LCROSS. This is not a application to all permanently shaded regions, but just an application to what was sampled there. Next, when we looked at impact and escape, what we found was the best fit was a combination of comets and then water contributed from the solar wind. So we finally had model scenarios that would actually fit. Thank you, Michael. Michael just posted that it's about 5 days per lunar orbit for being inside the magnetosphere, I think. I'm assuming, because I think it would be less. Okay, so moving on with clathrate formation, we were not able to get a good fit to the composition of the LCROSS plume, primarily because of the oxygen to carbon and carbon to hydrogen being so far outside of the bounds of what would be allowed for clathrates to be storing these volatiles. So we ruled out that the volatiles are stored as clathrates, and they are likely stored as just volatiles condensed onto the surface. So that is our next conclusion. Then we moved on to sublimation and recondensation, and this one was difficult to constrain, so we added 4 more elemental ratios to provide a better constraint for it, and these are shown here on the table. And from that, we got a combination of comets and chondrites at the percentage ranges that were shown here. So we had a slightly different answer from impact and escape. We didn't need any solar wind contribution of water to come up with measurements that were seen by LCROSS. And we got a combination of comets and chondrites and some sort of mix. Now, because comets are made up of ice and chondritic material, comets alone could explain the combination if we just focus on sublimation and recondensation fractionation. And then finally, we have the combination of escape, sublimation, and recondensation, and we again get a combination of comets and chondrites, which is our final model result for the origin of the volatiles that were seen by the LCROSS plume, taking into account the uncertainties on the measurements, the uncertainties on the sources, the composition of the sources, and the processes that could fractionate. We come up with the best explanation as comets and chondrites, and which comets alone, because of their refractory material, could explain. Now I see a question in the chat, what kind of volcano? Presumably interplate volcanoes would be different from volcanoes on continental margins. If you have a reference for the composition of gas that would come from those 2 types, it would be very helpful. The information that we used was the information that was available in the published literature. So I welcome any input on composition. The key thing, though, about volcanic composition is that it's just lacking in nitrogen, and there's just no way you can have volcanic gas introducing sulfur and introducing carbon and still end up with this much nitrogen in the LCROSS plume. So that's the main constraint, unless there is some sort of volcanic gas that has a lot of nitrogen that I wasn't able to find in the literature.
Hey, Kathy, I have a question. I didn't get the difference between this scenario and the previous one, submission condensation. Is it just the escape that you added there?
Yes, we just added the escape. We're ignoring clathrate formation because we concluded that the volatiles aren't stored in clathrates, so we don't need to take into account that process. Escape is included in both volcanic atmospheric processes and impact and escape. So by including that, we're taking into account all of the processes, except for sulfur in a volcanic gas being absorbed by the surface, and that would be elemental sulfur. So that's the only other thing that we're not including in this final model. And that's why we also have 4 ratios that are completely unconstrained, because the processes that we're considering counteract each other. And so we can't even use those ratios to constrain what the source would be. And that's why we had to add 4 more ratios to provide some better constraints on the results. Otherwise, we end up with a combination of anything could work. Does that make sense
Yes,
and answer
okay,
your question?
thanks.
Okay. Any other questions? Okay, so that brings us to our final slide, where I restate that nitrogen and sulfur are really the key elements for constraining the source of volatiles for this crater, this permanently shaded region, and this part of that permanently shaded region that was sampled. We have so much possibility in the future with in situ measurements to go much deeper and further with these types of studies and figure out really the history of volatiles on the moon as we start exploring these areas. We ruled out volcanic sources specifically because of nitrogen, and find the best fit is a comet, because you need cometary ice and chondritic material. Now, there could be also asteroids contributing or micrometeoroids, but you need a comet to get that ice composition and that nitrogen that is contributing to it. And then I just outline here future in situ measurements that we could really benefit from having for getting much better constraints on specific sources as we do exploration of the moon. So that is it. Any questions?
Awesome. Thanks, Kathy. And we have plenty of time for questions. Yeah, go ahead, Mike.
I have a comment more than a question, I think.
I guess
it's a question that I'm assuming will turn into just a discussion and not have an answer, I guess.
Yeah.
I'm wondering how refractory organics might fit into this. So like if you have ices and they're exposed to radiation or UV, they can cross-link and form chains and everything, and those might not have been detectable by the methods of the LCROSS experiment.
Yeah, that is a good question for the LCROSS experiment. For chondrites, the composition that we used was based on bulk composition, so it does take into account the chondrites, the organics and chondrites. But yes, the biggest limitation of the study is what we were able to measure. Another example of something that could be missing is studies of impacts of comets and asteroids on the moon that have simulated the composition of the volatiles that would be produced by that impact, show that nitrogen preferentially forms N2 in an impact, which
that
means
was another thought.
Yes, and that means that N2 could have been in the LCROSS plume, but with the instruments that we were able to use to measure it, the plume, they did not have the capability to measure N2 because N2 is really hard to see remotely. You have to basically measure it in situ. So we saw a huge amount of nitrogen relative to carbon in the plume, and we were probably missing a lot of the nitrogen that was actually there. So there was probably even more nitrogen in the regolith than what was seen by LCROSS.
And I see Carly has her hand up.
Yeah.
Unmute. Okay, great talk. So many things to think about. And of
Yeah.
course, I didn't absorb it all. So consequently, my question. One of your conclusions about the best fit is of cometary ice and chondritic material, and that makes sense. The question is, that also implies that it would have to accumulate over multiple events. And that would require a lot of stirring and timing, and I would expect processes involved in just that accumulation that would be hard to constrain. You know, this gets back to fractionation and escape and all these other things, which you've addressed, but is required in the cometary and chondritic combination.
Yes. And we have tried to address those processes, like basically accumulating volatiles over time from multiple sources, multiple impacts. Now, these impacts could have happened into the PSR, or they could have happened at a distance from the PSR and then the volatiles migrated. And we've tried to take into account the processes that would fractionate the ratios by taking into account atmospheric escape, because during the process of transport, you would lose volatiles from escape from the atmosphere. And then the recondensation and sublimation, we also used that to try and account for specifically the process of micrometeoroids impacting the surface on an ongoing basis and stirring up the volatiles and releasing some, such that the volatiles that have a lower volatility temperature are less likely to return to storage in the permanently shaded region, where water, which has a higher volatility temperature, is more likely to be retained through that process. So we've tried to account for that through those two fractionating processes.
Cool. Yeah. Thanks.
Yep.
All right, what other questions do we have for Kathy?
This is Jen. I have a quick question. So just thinking ahead for the future measurements. So you call out, you know, in particular, sulfur and oxygen isotopes would be valuable for getting at the origin. I think we all understand and know why, but I've also heard it argued that, you know, there's been so much processing of these materials over billions of years that the signal has just been so convoluted that we can't ever back out the origin based on isotopes. So I'm just wondering where you stand in that debate. What do you think about that?
Yeah. I think it's very important to keep that fact in mind once we do have these measurements, and to take it into account. The noble gas abundances are particularly interesting because we've recently gotten measurements of noble gases and their isotope ratios from one comet, 67P, and that was the one that was orbited by Rosetta. And what really stands out about their measurements is specifically the xenon isotopes. They are ridiculously different from anything else in the solar system. So if this is representative of cometary xenon, then you could use the measurements of the xenon isotope patterns to determine the amount of contribution of cometary volatiles, or at least cometary xenon, and then apply that to the other volatiles through modeling. So I think what would be important with isotope measurements is to focus on ones where there are clear tracers. Another example is the krypton isotopes. The measurements that were made by Rosetta of the krypton isotopes were pretty close to solar. So we can't learn much from studying krypton in comets. And so focusing on the krypton isotopes could be a waste of time, whereas focusing on xenon isotopes could provide very useful information. And then helium isotopes are also pretty interesting because those vary throughout the solar system quite significantly based on their source material and the age that they were deposited in that material. So I think knowing the isotopic tracers across the solar system and then knowing which ones to focus on is going to be really important as we move forward and start making these measurements. So we need inventories, and we need studies and databases of these inventories.
While folks are thinking, I can ask another question. In fact, I can ask two more, but I'll just ask one. So, yeah, this is super interesting, Kathy, to see the how certain elements can be really diagnostic. In terms of, so thinking about this from a remote sensing perspective, so both orbital and landed, but looking at it, spectroscopically, are there any particularly diagnostic molecular species associated with that nitrogen and sulfur that would be good to look for?
Well, I think ammonia is something that might be possible remotely. I don't know from orbit, because Lizeth has done some really good work with the LAMP data, really pushing it to its limits. And it's really difficult to get clear detections of anything other than water, but there's possible indications of other volatiles contributing. Constraining what they specifically are is really challenging from orbit. In situ measurements or measurements from the ground remotely could be better. My personal preference is mass spectrometers, though, because that's going to get volatiles that are impossible to measure remotely, specifically noble gases, and it will get it. It's the only way to get the isotope ratios as well. It's the only really reliable way to get N2 if you have enough mass resolution to separate it from carbon monoxide, because they're both at the same mass. And then getting the isotope ratios of nitrogen would be really good, because you combine nitrogen in D to H, and you've got a really good tracer for the sources as well. That's been used for the Earth's delivery of water to the Earth for some time now. So mass spectrometers.
And then the sulfur, would that probably be SO2 or?
I have to admit, I don't know enough about remote sensing to know how easily H2S or SO2 would be detected on the surface if it's like just condensed onto the surface.
I want to say SO2 has some strong lines if you go far enough into the infrared.
Okay.
Most of our spectrometers don't go quite far enough. Most of our flight stuff doesn't usually get that band, though.
Okay.
Cool. We have time for one more question, if someone wants to take the last one.
I'll throw out there that there is a NH stretch that is kind of in the same 3 micron region as the OH and all the various something H stretches are. But it'd be difficult to build up a case for, from that thing alone, it'd be difficult to build up a case for this is specifically NH and not, OH in a different matrix or similar.
Yeah, because I think you'd have to have a lot of NH compared to OH.
So I have a question. Did you consider, for the future study, I don't know, the contribution from the Earth nitrogen ions? Because
good. Go ahead and finish.
I was thinking about the relatively recent detection of oxygen ions from Kaguya.
Yeah.
So I wonder if the
Um,
same thing applies to nitrogen.
Yeah, I did actually look into that. And from studies, I believe it might be from Apollo samples, maybe even looking at isotopes. I saw a paper that talked about terrestrial nitrogen on the surface of the moon in the regolith, and the theory that they put forward as the source for that was that nitrogen ions were transferred from the Earth to the moon before the Earth had a significant magnetic field. I think that was it. It was something to do with the development of the magnetic field. And the time period that they gave for that delivery of nitrogen from the Earth to the moon, and I'm probably screwing up this stuff on the magnetic field, but the main thing I focused on was the time period that they gave was before the age of the Cabeus crater.
Okay.
So that nitrogen has to be too old to be a recent enough source for the nitrogen that we observed in the permanently shaded region.
Okay, makes sense. Yeah.
Yeah. But yes, I did think of that because I was looking at all this nitrogen. I was like, I need another source. Where is this nitrogen coming from?
So I
Okay,
think
thanks.
the Artemis has quantified that, the original Artemis, not the new one that HEMOD is doing.
Yeah.
But so they've quantified it for present day transfer from the Earth to the moon, I think.
Yeah.
Looks like a Poppy 2016 might have that in it.
I will look
Andrew
that up.
Poppy.
Okay.
All right,
Well,
so
One
We-
quick comment, if
Yeah,
I
go
could,
ahead.
just at the end.
go for it, Jeff.
This conversation and all the things that Kathy has been talking about has really been stimulating. And I realize it's sort of been alluded to in the discussion that Trailblazer is going to be going and looking in the permanently shadowed areas with spectrometers up to 3.6 microns. And we do know what sort of is in there, but we don't have all that good laboratory data of some of the processes we've been talking about, you know, the
Yeah.
churning and what actually is likely to be on the surface and in a combination that Trailblazer can detect. It would be really
Yeah.
nice to have that before we go there.
Yeah, that's a really good thought. Definitely worth thinking about.
Maybe you can model it.
Yeah. Let me because Rachel's just across the hall from me, Rachel
Yeah.
Klima. I can touch base with her and find
Good.
out what she thinks of that and see if
Yeah.
there's some way that I can help with that. That
Good.
would be really cool.
Yeah. Great.
Yeah.
Yeah, very cool. And I'll run down to your end
Yes.
of the hallway as well to join in
Exactly.
that discussion.
Yeah.
All right.
We're actually in
Well-
the same building right now.
All right. So on that exciting note, thanks again, Kathy. That was a great talk, super interesting, and we'll all keep an eye out for the paper when it's out in
Yep.
its final published version.
Great.
But yeah, thanks for a great presentation, Kathy. Thanks everyone for joining in and having keeping a great discussion going. And with that, we're a couple of minutes over the hour, so we'll wrap it up quickly. But we will not be meeting in December. So enjoy Thanksgiving, enjoy your holidays. And we will meet again sometime in the new year.
Safe travels to India.
Thanks, Jim. Take care, everyone.
Stay safe.
Bye-bye.